All right, guys, welcome to section 2.4. This is our last section in chapter 2 that we're going to look at. And this one's all about angle properties of polygons. All right, a polygon is just any shape that has a certain number of sides and angles to it. And we're going to deal strictly with um, regular polygons, okay? So that means every side and every angle in it will be equal, okay? So that's what you need to remember there. Equal side lengths and equal angles. The first term that I want to go over real quick with you guys before we get into this is the difference between an exterior and an interior angle. Okay? An interior angle is any angle inside the polygon. Okay, now as you can see, this example that I have here, this is not a regular polygon. Why? Because these angles are clearly different. They're not all equal. Okay? And these lengths here, these two lengths are probably the same, but these ones are different. So this is not a regular polygon. So the green angles here, these represent the inside interior angles, okay? Now, what I'm going to do here is I'm going to erase one side of the polygon, or at least all my scratch marks, and I'm going to show the interior angles in blue. All right, or sorry, the exterior angles. No. The exterior angles are the angles that are formed on the outside of the polygon by extending one of the lines. Okay, it's like this or like that. And by doing that, there we have these angles here. And these are my exterior angles, okay? We talked a little bit about, ooh, where'd that go? Exterior angles before. There we go. When we talked about properties of triangles, okay? There we go. That's better. All right. When we talked about properties of triangles, I remember um, an exterior angle is equal to the sum of exterior or the sum of opposite exterior angles or interior angles. Sorry, we talked about that with triangles. Remember, if I drew a triangle, oh, I didn't want to do that. Sorry. So let's say I wanted to draw. If I had this triangle over here, this exterior angle is equal to the sum of these two um, opposite interior angles. We talked about that in 2.3. So now what we're going to do is we're going to look at polygons, and remember, regular polygons. So that means the angles and the sides all have to be equal. Not necessarily um, all the sides have to be equal to the angles or anything like that, but all angles have to be equal to one another, and all sides have to be equal to one another. So let's take a look here at our first example. So what we want to do here is we want to determine the measure of each interior angle of a regular 17-sided polygon. Now, in middle years geometry, you would have talked about different things like what a pentagon was, what a hexagon was, what a heptagon was, what an octagon was. You probably might have went up to 10, 10 being deca. We never covered anything. You've never covered anything to deal with like 17-sided polygons, 22-sided polygons. I'm not going to try to draw one here because they start to get a little ridiculous. Um, but we can find the measurement of the interior angles. Does this thing draw them? Oh. So, the biggest that I can draw, that's a 16-sided polygon. All right, and I'm not actually drawing it. That's coming from what's given to me on computer program here. There we go. Okay, so that's 16-sided. It almost looks like a circle, but what we want to do is we want to find the sum of each little angle here. Each one of them. So there's 16 of them all together, and we want to find the measurement of each one and then add them all up. Okay, so to do that, you need to use this formula that's given up here, 180 times n minus 2. All right, so what this formula is, 180 times n minus 2. Okay, so what you do, n, really nice to work with, is just number of sides. So you just take the number of sides your object has, you subtract 2 from it, and you times that by 180. And that gives you the sum of all your sides. Okay, so if we do that, I'll do that over here in red. I'm just going to go S equals 180. And I know my n value here. It's 17. And I'm going to subtract 2 from that. So real quick, I'll show all my work here just so you guys can see it. 17 minus 2 is 15. And then you just go 180 times 15. Let's see here. Let me get my calculator out. So that's 2,700. So my sum equals, whoa, what's going on? Sorry about that. Sum equals 2,700. So that's now the sum if I took every single angle from my 17-sided polygon and I wanted to know what they were when I added them all up. But what I'm looking for is the measurement of each angle individually. So now if I have the total of all 17, what I do is I take that sum, and all I'm going to do is I'm just going to divide it again by n. Now just be careful you don't use n minus 2, because if you do that, you're basically just going back and taking 180, timesing it by n minus 2, and then dividing it by n minus 2, so you're going to end up with 180. So I'm going to take 2,700, and I'm going to divide it by 15. And that's going to give me the measurement of each angle. So I'll do that on my calculator. Oh. Make sure I write that down properly so you guys don't make any mistakes. 2,700 divided by 15, or 17, sorry. And that's going to give me 159 degrees. And that makes sense if you look at your shape here. Each one of these angles is definitely obtuse. It's more than a 90 degrees. So they should be bigger, and which it is, 159. Now the actual answer is 158.8, but when you're dealing with angles like this, just round to a whole number. It's totally fine. All right, so that's example 1. All right, example 2. Now we want to show the sum of the exterior angles of a pentagon is 360 degrees. So pentagon, penta meaning 5. See if I can draw one here using the power of technology. That one worked out quite nice. So now what I want to do is I want to find the sum of the exterior angles. So my exterior angles now, remember, are the ones on the outside, and you get those by extending your lines. So this one, that one, that one, this guy, and this guy. Now I could have went the other way too, and I could have drawn this way, and that way. It's up to you. As long as you're consistent, it doesn't really matter. Just make sure if you're going in one direction, you keep that consistent, okay? So I have these, and if you look, I have 1, 2, 3, 4, 5 sides and I have 5 interior angles. So that also means I'm going to have 5 um, exterior angles as well. So now I want to deal with finding the sum of these exterior angles. And if you look, I haven't given you any formulas for that. I know that the sum of the interior angles is 180 times n minus 2. And I know if I want to find the measurement of an individual angle, so I know for a angle, it's 180 n minus 2 over n. So if I use this formula here, that's going to give me this guy here. Now what's nice about this, if I extend all these lines, right, the angle of any straight line is 180 degrees. So I know that my exterior angle plus my interior angle, ooh, I don't know why it's doing that, is going to equal 180 degrees. So if I can find one interior angle, I can then find the exterior angle, and then I could just multiply it by 5, and that's going to give me what the sum of all my exterior angles are, which I'm looking for here, the sum, and I'm hoping that it's going to turn out to be 360 degrees. Fingers crossed. All right, so let's work that out. So I know that an angle for any regular pentagon or any regular polygon period is going to be 180, 5 minus 2, because I'm dealing with a pentagon, so my n is 5, divided by 5. Now this time I'm not going to show all my work. I'm going to trust that you guys can just do this with your calculator. So you'll go 5 minus 2, because remember BETMES, you do the brackets first, your order of operations. You're going to multiply that by 180, and then you're going to divide that by 5. And there you go. You should get 108 degrees. So that is this guy here. So that's 108. I know my exterior angle is just going to be 180 minus 108. Which is just 72 degrees. So now I want to show that the sum of all the angles is going to be 360. So hopefully if I go 72 times 5, because I have 5 exterior angles, look at that. 360 degrees. This system works. I love it when it works out quite nice like that. All right. So with that being said, what's nice about that is, we go over to the next page, the sum of the exterior angles of a regular pentagon is always going to be 360. So that means the exterior angle of any pentagon of any regular polygon is 360 divided by n. Okay. Now let's look at the next one here. What type of regular polygon has an interior angle 3 times the exterior angle? Ooh, good question. Well, what's cool about that is we know that the sum of exterior angles has to equal 360 degrees, because that was what's stated in the rule above. And we know, due to this question, that the interior angles is going to be 3 times that of the exterior angle. So if the exterior angle, if you add up all their sums, is 360, that means the sum of the interior angles let's try that again. The sum of interior angles has to equal 3 times 360. So if I work that out, I go 3 times 360. That's going to equal 1080. All right. So I know my interior angles now add up to 1080. Now, if I know that, I also know based on example 1, that the sum of my angles equals 180 times n minus 2. So if I have my sum, now I need to solve for n. So I would say that 1080 equals 180 n minus 2. So what I'm going to do here now is I'm going to solve for n. So I'm going to take 1080, I'm going to divide both sides by 180. Okay. So that's going to give me, 6 equals n minus 2. So if I add 2 to the other side, n equals 8. All right, so that means I have a regular polygon with 8 sides, so I have a octagon. Okay. That could be my most favorite gon to say in the world, octagon. It just kind of rolls off the tongue. All right, now for the last example here, what we do is we have a floor tiler, and he's trying to get really fancy with tiles that he's laying on the ground. And he's laying down regular polygons, so 5-sided objects. Oh, sorry, I read that wrong. He's laying down regular polygons. Can the tiler use regular hexagons and equilateral triangles to tile the floor and have the same side length? So if you had a hexagon, now there's no way I'll be able to draw these perfectly that they line up. And a regular polygon. And assuming that they were the same size, could you lie them side by side? Like this. So what you would need to do, now assuming they're all the same length, I'd have a regular triangle in there as well. Something like that. Could I get those all to line up? Now, sorry, those are supposed to all be the same size, but they're not. But that's okay. With the power of imagination, we can believe they are. So what we need to do is we need to check our 4 angles here and make sure they add up to 360. So we don't have to do it for all of them. We know we have 2 hexagons that are the same, right? And we know we have 2 triangles that are the same. Right? 2, 2, 2, 2. So what we do is we just take, and what we do is we find the measurement. We find the angle measurement for the hexagon, and we'll find the measurement angle for the triangle, and then we can solve. So for the first one, for the hexagon, we know the hexagon is 6, so we know this guy n equals 6. So I know that one measurement is going to be, one angle would be 180 times 6 minus 2 divided by 6. So 180 times 4, that's 720 divided by 6. So 120. So I have 2 of those, so I have 120 there, and I have 120 there. So if I times that by 2, that's going to be 240. So now what I need to do is I need to check what the measurement of my angle is on the triangle. Now what's nice is I know I have an equilateral triangle, so that means all 3 angles of a triangle have to be the same, right? So that means this angle here would just be 180 times divided by 3, which is just 60. And since I have 2 of them at each top where they cross or where they intersect, so that's going to be 120. 240 plus 120 is 360 degrees. And since this then makes a nice, oh, what happened there? This makes a nice round circle right here where they intersect, then that means yes, he can. All right, and those are the examples for lesson 2.4. I hope that makes sense. If not, make sure to ask questions. All right.